We're going to talk about integration by parts today, and it's another technique of integration, and it has to do with the product rule for derivatives. So if you think about the product rule for derivatives, we say if we have two functions that are multiplied together, f of x times g of x, then the derivative of that is f of x g prime of x plus f prime of x times g of x. That's the product rule, and we're used to that. And what we typically do is in order to try to figure out how does that relate to integrals, is we integrate both sides. And so that's what we're going to do. And if we integrate both sides, it looks like this. Okay, now the integral of f of x g of x prime, this part, is just going to be f of x times g of x. So we write it like that, and we just put a plus c because the constant derivative of constant is 0. So we always put a plus c when we do an indefinite integral. And then what we're going to do is we're just going to take these two integrals, and we're going to take one of them and pop it to the other side. Okay, so we're going to take this guy and move it over. And what we do then is we write it like this. So we have f of x, the integral of f of x g prime of x dx. That's, I switch sides. And then it's f of x g of x minus this. And you might be wondering, okay, where did the constant go? Well, it's now part of this integral, because when I integrate this, it's going to give me a plus c, and I can add it to the constant that was from here to just get another constant. So it's swallowed up, sort of, for lack of a better term, into this integral. So this is the premise of integration by parts, that if you have two functions that are multiplied together, what you do is you say, okay, well, we're going to treat one of the functions as f of x, and we're going to treat the other one as g prime. And then doing that allows us to then create another integral. We take f of x times g of x, but then we go minus f prime g of x dx, and often this integral is able to be integrated when this one has not or is not. Okay, has not been able to or is not able to be done. So we write this a little bit easier in terms of notation by replacing f of x with u and g prime of x dx with dv. Okay, so then we get u times v minus the integral of v du. Okay, where this f prime of x dx is the derivative of u if u is f of x, and this g of x is the integral of v. It's v, or the integral of dv, sorry, which gives you v. So when we write it out like that, we get this statement: the integral of u dv is equal to u times v, sorry, minus the integral of v du. And what it's allowing us to do is integrate a product. That's what we're trying to do. So let's do an example. We have here the integral of x e to the x dx, and the first thing is to look at the integral and say, well, how do I know that it's integration by parts as opposed to u substitution, or as opposed to just a simple integral? And the way we know that is by looking at the form of the integrand, because if you look at x e to the x, first of all, it's not able to be integrated right away, because we know the integral of e to the x, and we know the integral of x, but we can't do it as a product. So immediately when we have a product, we then try to say, okay, well, can we use u substitution? And if you use u substitution, the only thing that you can let u equal is x, and you're just going to end up with u e to the u. Like, it's not going to help you to do u substitution. So if you have a product, and the product is such that you can't use u substitution, then you do integration by parts, or you try integration by parts. And to do that, you need to make two choices. You need to choose a u. In other words, one of the functions has to be u equals that function, and the other function has to be dv. All right, so in our case, I'm going to let u equal x, and I'm going to let dv equal e to the x dx. Now you might be wondering, well, why? Why did you make that selection? What I'm trying to do, first of all, is I'm trying to take any piece of the integral that you can't integrate, that has to be u. Because what we're going to then do is we're going to take the derivative of u, because we're going to find du, but we're going to integrate dv to find v. So if you can't integrate a part of that, like for example, if it was ln x, we don't have an integral for ln x, so u would have to be ln x. Here, though, both of these, x and e to the x, we can integrate them. The integral of e to the x is e to the x, and the integral of x is x squared over 2. So we can integrate them. So then why did I choose u to be x and dv to be e to the x? Well, after you've decided, yes, I can integrate both, then what I do is I try to figure out which one's derivative is going to get smaller, because what we're trying to arrive at is an integral here that's easier to integrate, or even possible to integrate, when this is not. So if I let v and du in here be things that are going to be smaller, in other words, they're going to decrease this, then that makes me happy. So if I let u equal x, then du is just going to be 1, or just going to be dx. So it's getting smaller. If I let u equal e to the x, the derivative of e to the x is e to the x, so it's not going to get any smaller. So it doesn't help me to let u equal e to the x. So these choices, the choice of u and dv, are motivated by a, u is equal to the thing that you can't integrate, the piece of the function that you can't integrate, if there is one. And then after you've decided, no, that's not the case, both things in there, both parts of the product can be integrated, and then I say, okay, what's going to get smaller when I take the derivative of it? Okay, so here it's x, so then I integrate this, all right, I integrate dv to get v. So the integral of e to the x dx is e to the x, and I take the derivative of this part, which we're used to from u substitution, so du just becomes dx. And then what I do is I follow the format. So I say the integral of x e to the x dx is equal to u times v, so it's going to be x e to the x, and then minus the integral of v du, so minus the integral of e to the x dx. So that gives me this. And that's just filling in the formula. And again, we arrived at that formula by using the product rule for derivatives and integrating both sides. And so then what we do is we say, okay, now can I integrate this? And sometimes you can right away, like we can here. Sometimes you might have to do parts again, or you might have to do u substitution, or you might have to do something else with that integral. But for now, the integral of e to the x is just e to the x. So I get x e to the x, there it is. The integral of e to the x is e to the x, and then I have a plus c. So the integral of x e to the x dx is x e to the x minus e to the x plus c. And again, just like with any integral, you can check your answer by dividing, or by taking the derivative, sorry, not dividing. So I can take the derivative of this, and I can see if it gives me that back. So this is a product rule, so it'll be x times the derivative of e to the x, which is e to the x, and then plus e to the x times the derivative of x, which is 1, minus the derivative of e to the x, which is e to the x. And so you'd end up, if you take the derivative of this, you'd get x e to the x plus e to the x minus e to the x. Those cancel, and I'm left with x e to the x, which is what I started with. So it is correct. Okay, so that's how integration by parts works. So let's just look at another example. All right, here's an example where I have x squared and then e to the minus x dx. And I say, okay, how do I do that? Well, again, you try to do u substitution if you can, but you can't because the composite function is minus x. And if you let u equal minus x, then you're going to run into a problem here. So we just let the integration by parts formula dictate what we do, and we're going to make a choice. We're going to make a choice of u and dv. I've chosen u to be x squared because the derivative of x squared is 2x, so it's going to get smaller in terms of the degree. And e is a function that just e to the minus x. You can integrate that, take the derivative of it very easily. So we're going to just, and it's going to stay the same, essentially. It's just going to change sign. So we're going to let u be x squared and dv be e to the minus x dx. So if I do that, then this is what I get. If u is x squared du, the derivative of u is 2x dx here. The derivative of u and the derivative of x squared. Then here I integrate dv to get v, and I integrate e to the minus x dx. And the integral of e to the minus x is e to the minus x times minus 1. Okay, and the minus 1 is just correcting for the negative in front of the x. So then I plug into my formula and I get this. Okay, u times v is minus, well, it's x squared and then minus e to the x as to the minus x. So that's where I got that term from, minus x squared e to the minus x. And then the other term is v, which is e to the minus x, and du, which is 2x dx. And what I've done, because it's negative here, and the formula says minus the integral of v du, I've changed it into a positive. Okay, because the minus from the v and the minus there gives me a positive, and I've taken the 2 from du and just put it out front. And what you'll notice is this integral now looks very similar to the one we just did, x e to the x. The only difference is it's e to the minus x. So we actually, for this integral, we have to apply parts again. So we let u equal x, so du becomes dx, and we let dv be e to the minus x dx, which means that v is minus e to the minus x. It's the integral. This is the derivative. So integral here, derivative there. So then this stays here, the minus x squared e to the minus x, but then I go u times v and integral of v du. And the whole thing is multiplied by 2 because the 2 is outside of the integral. And then what I do is I say, okay, now I can integrate this. I can integrate e to the minus x dx, and it gives me minus e to the minus x. So I end up with this. And then I'm just going to multiply the 2 in there to get this. So I get x squared, minus x squared, sorry, e to the minus x minus 2x e to the minus x, and then minus 2 e to the minus x plus c. And what I notice is that there's an e to the minus x in all 3 of those terms, and they're all negative. So if I take that out as a common factor, then I'm just left with that. And again, we could take the derivative in order to try to figure out, did we do it right, or does it give us the right answer? Okay. So you can do that on your own. You can check your answer if you wish to. But that is integration by parts, and I'm going to cut the video there, but there's a few other examples that we'll go over in class.